All right, let's dive right into this explainer and build a really concrete framework for evaluating GPUs. And we're going way beyond those superficial marketing numbers today. Look, if you've ever tried to provision hardware for AI, high-performance computing, or even just a heavy-duty workstation, you already know the spec sheets can be absolute noise. So today, we're going to learn exactly how to cut through that noise and evaluate hardware holistically.
You know, it's super tempting to look at a spec sheet and just assume that a higher core count or some massive VRAM number automatically equals better performance, right? But the reality is so much more complex than that. A GPU that looks incredibly fast on paper can actually bottleneck your entire system if it's just the wrong fit for what you're trying to do.
Here is our roadmap for today. We're going to cover the GPU evaluation trap, break down the 4 performance layers, figure out how to avoid bad comparisons, do an A100 versus H100 showdown, and then wrap it all up with a very practical buying workflow.
Okay, kicking things off with Section 1, the GPU evaluation trap, and exactly why judging by the spec sheet fails. Here's the absolute golden rule. A GPU's usefulness entirely depends on how its compute, memory, interconnect, and software actually align with your specific job. You really cannot judge a GPU in isolation. The exact same piece of hardware can be an absolute game changer for one project and a total roadblock for another. At the end of the day, it is all about the fit.
Context is literally everything here, because each task weights the hardware totally differently. Take AI training, for example. That workload craves tensor throughput and memory bandwidth. It honestly doesn't care at all about ray tracing cores or hitting a high boost clock. But conversely, if you're building a workstation for 3D rendering, you're going to prioritize those exact things that the AI just ignores. So you have to define your workload before you even start looking at a GPU.
Moving right along to Section 2, the 4 performance layers. Let's look beyond the headline numbers.
Our first layer is compute, and honestly, this is the biggest trap because it's where everyone looks first. But more cores do not automatically mean better performance. Why? Because you might be dealing with the wrong precision support. Think about it. If your GPU has massive FP32 throughput, that is awesome for gaming graphics. But if your HPV simulation actually requires double precision FP64, or your AI model desperately needs dedicated tensor cores, well, those extra raw cores won't do a single thing for you. Now, we hear a ton about VRAM capacity, but is a larger VRAM actually going to help if the memory bandwidth is bottlenecking your data? No way. Large AI models, high-res visual assets, and data-heavy workloads usually fail not because they run out of space, but because the data simply cannot move fast enough between the memory and the compute cores. Think of capacity like the size of your gas tank, and bandwidth as the fuel line. Both of them have to be big enough, or your engine is going to starve. Layer 3 is interconnect and scaling. Because let's face it, once one GPU isn't enough, scaling suddenly becomes a massive part of your evaluation. You will quickly learn that standard PCIe lanes are great and flexible, but they are absolutely no substitute for dedicated accelerator fabric like NVLink when you're running massive multi-GPU training jobs. If your multi-GPU communication overhead starts dominating the processing time, slapping more GPUs in the rack actually gives you diminishing returns.
And layer 4 is efficiency and deployment fit. A GPU might look like an absolute beast on paper, but if it melts your server rack because it exceeds your cooling capacity, or it completely ruins your performance per watt budget, you've got a major problem. In the real world, picking a slightly slower but significantly more efficient model is usually the much smarter, more stable choice for a production environment.
Okay, Section 3, avoiding bad comparisons. Let's talk about how to navigate through all that marketing noise.
Marketing departments are literally optimized for attention. They want you to look at a consumer GPU with a massive boost clock and think, wow, that's a beast for everything. But ignoring sustained power limits, a lack of precision support, or weak memory bandwidth, just because a consumer card looks fast on paper, that is a recipe for disaster if you're operating in an enterprise or AI environment.
So what's the fix? You've got to turn our 4-layer framework into a weighted score. Notice how something like AI training heavily weights VRAM, memory bandwidth, and scaling, while an HPC workload shifts the focus way over to FP64 and NVLink. Meanwhile, rendering is prioritizing CUDA throughput and ray tracing. The trick is to ensure you are grading the hardware on the exact metrics your workload actually demands, and literally just ignoring the specs that don't apply to you. Let's put this into practice with Section 4, the A100 versus H100 showdown, applying the framework to some real enterprise giants. Applying our framework to the A100, we immediately see that it remains an absolute powerhouse.
It has a super robust compute profile tailored directly for AI and HPC, incredibly high memory bandwidth, and excellent NVLink interconnect support. It completely proves that true evaluation reveals immense value far beyond a standard consumer spec race. This thing was built from the ground up for the data center, and its operational fit reflects that perfectly. And then we have the H100. Now, listen, the H100 isn't just an A100 with bigger numbers patched onto it. It is a comprehensively re-architected system. It features substantially stronger tensor acceleration and vastly improved system scaling, meticulously optimized for the massive demands of current-generation large model AI workloads. By comparing them directly across our specific layers, the true picture really emerges. Yes, for sure the H100 dominates newer AI workloads. Just look at that memory layer. The H100 leaps to over 3 terabytes per second of bandwidth compared to the A100's roughly 2 terabytes per second. That is a massive game changer for memory-bound tasks. But depending on your exact budget, your existing cluster setup, and maybe your mixed-use requirements, the proven efficiency and the established platform fit of the A100 might actually still make it the smarter choice for your specific deployment.
All right, bringing it all together with Section 5, Practical Buying Workflow. Let's make this actionable.
By strictly following these 6 steps, you can completely bypass the marketing hype. First, you define your job and find the actual bottleneck. Second, you weight the specific parameters that matter to you. Third, compare your candidates across our 4 layers. Fourth, verify the physical and financial constraints of your deployment. Fifth, always check the software drivers. And finally, sanity check against real-world benchmarks for your specific task. That's how you guarantee you're matching the entire hardware ecosystem to your actual operational needs. If you take nothing else away from this explainer, keep this minimum mental model in your back pocket. A GPU is a deeply integrated system. Every single layer, compute, memory, interconnect, and efficiency must seamlessly align with your specific task. And never forget that marketing claims are designed to grab your attention, not to evaluate system architecture.
I absolutely love this thought, and it all comes back to this. The better GPU is the one that best fits the job, not the one with the loudest headline number. We've seen how ignoring memory bandwidth just to chase core counts or ignoring scaling fabrics for raw clock speeds leads to incredibly expensive mistakes. It is all about the fit. I really hope this framework empowers your future evaluations. And I'd invite you to test this logic against whatever hardware you're currently running right now. Because the next time you are staring down a massive, crazy expensive spec sheet, you really need to ask yourself, are you just buying a headline or are you actually buying the perfect fit for your bottleneck? Think about it and start evaluating holistically.